A derelict site, recently acquired for development. But before the JCBs can move in, the geotechnical team has work to do. A number of exploratory boreholes are to be drilled.
Okay, we'd like this one 12 metres out from the lamppost.
The drilling method to be used will depend on a number of factors, particularly on what's already known about the ground and groundwater conditions. As the team marks out the boreholes, it also evaluates hazards before drilling starts.
That's borehole 11, Dave. That's 12 metres out from the lamppost. No underground service is marked, and we're okay for overhead cables, so it's okay to drill in that position.
On this occasion, the decision was to use shell and auger for the site survey, a technique widely used in the UK for drilling and sampling in soft ground.
Come on back! Whoa, that's okay there!
The light portable equipment allows it to drill in places inaccessible to heavier gear. A broad view of the ground and groundwater conditions has already been determined in a depth study, but now further exploration is required to allow suitable foundations to be designed and the method of construction for the new building to be decided. The overriding consideration is value for money, and the team will deploy the most cost-effective means of gaining the information they need. This program will look at the three most common techniques used for drilling in construction and environmental projects. They are shell and auger, rotary drilling, and continuous flight and hollow stem augering. For later reference, you'll find relevant points about each of these in the notes which accompany the program. But to start with, we'll continue our look at the shell and auger technique. Shell and auger uses equipment which is relatively cheap and easy to maintain. Although this survey only requires sampling to a depth of 15 metres, this type of rig will allow boreholes to be drilled to 60 metres or more in suitable ground conditions. With the rig safely erected, the drill string is assembled. This consists of a hollow shell and a clay cutter at the bottom. The shell is allowed to fall under gravity. The surface material in the shell is collected. Once a certain depth has been reached, it will be bagged and sent off for analysis. The bars mounted above the shell are known as sinker bars. These add useful weight to the cutter. And as the hole is deepened, so the sample of collected material is added to. There is now half a metre's worth of sample, and the point has come to bag it. As in all survey work, accurate labelling is of paramount importance. This chisel can be used in place of the clay cutter to advance the hole through any hard layers or boulders. It's also used for proving bedrock. With the clay cutter, they've reached a depth at which the sides of the hole might collapse.
.3, we'll put the first lump of casing up.
To support the hole, they're going to install steel casing. The black piece at the bottom is a cutting shoe. The shell and sinker bar are used to drive the casing down to the bottom of the hole. With the casing right down, the pin is removed, allowing the cutter to continue excavating. As the depth of the borehole increases, more lengths of casing are added and driven down to extend the support. And not only does the casing prevent material collapsing inward, it's also a benefit if the borehole passes through water-bearing strata. Then it stems the flow of water into the hole, helping to keep the bottom dry and undisturbed, so improving sampling. Up until now, the team have been taking disturbed samples. These are useful for describing and classifying the ground, but they give no indication of strength, consolidation, or other such data. It's then that undisturbed samples are required.
You can see, John,
And it was on that subject that John Cripps from the Department of Earth Sciences at the University of Sheffield spoke to Bob Risby, a director of Geotechnical Engineering Limited.
we walk it over, we can put the peg in the ground.
Right. Well, Bob, we're now ready to take a sample. Would you like to take us through the way that we do that?
Yes, John, the sample we're going to take now is an undisturbed sample, and it's 100mm diameter, referred to as a U100 sample. This is a typical U100 sample tube. This particular one is made of aluminium. The assembly is as we see on the ground here. We start off at the bottom with a cutting tube. This is attached to a core retainer.
And this has little flaps then that stop the core from dropping out of the tube once it's been taken.
Yes, that's right, John. As the tube is driven into the ground, these little flaps close like that, allowing the sample to pass up inside. As the tube is withdrawn from the ground, these little windows open, retaining the core inside. This is the sample tube that we're going to retain our sample in, and as you can see, we've actually connected on this one an additional sample tube. The reason is that any cave-ins in the bottom of the borehole we want to be retained in the top sample tube so that our bottom sample remains completely undisturbed. And this entire assembly will be driven into the ground using the sliding hammer that you see here, and on the bottom of this sliding hammer we have a non-return valve assembly which is connected to the top of the sample tube. This non-return assembly allows liquid or air inside the tube to be expelled through these little holes, but when the sample is withdrawn from the borehole, nothing can actually get back in.
The U100 sample tube is about to be deployed. The sinker bars are attached to the top of the sliding hammer. To ensure the sampler isn't driven down too deeply, the operator adds a mark 600mm up, which you recall is the length of the sample tube. The sample collection begins. The sampler is progressively driven downward with the object of obtaining as undisturbed a core as possible. It's driven from the top by the sliding hammer arrangement. As the core moves up the tube, so the air and maybe water which builds up behind it is vented through the non-return valve. This allows the air or water to escape, but prevents anything from flowing back in. Skill is required by the operator to avoid lifting the hammer too far and jerking the sampler upward. Once the sample tube has been driven down to its full length, it's time to recover the core. And there's the bottom of the core. In this case, the core did not fill to the top. Nevertheless, the sample tube is capped to preserve what core there is. To provide enhanced preservation, something in addition to the metal cap is required. Melted wax is used to seal the end. The wax soon hardens, and again the requirement for careful labelling is paramount. And because the material recovered in the cutting shoe and core catcher might also be valuable for site analysis, a sample of that is collected. Laboratory tests on U100 samples can be used to give information about the strength of the ground, but in granular conditions it's not possible to collect cores. It's then that another technique is used. This is a split spoon sampler. It's going to be used for a standard penetration test, or SPT. The test is used to measure the strength of the ground in situ. It involves using a drop hammer of standard weight. The operator adds 6 marks to the drilling rod above ground. Each mark is separated by 75 millimeters. Once the weight reaches a standard height, it's released automatically. The essence of the test is to count the number of strikes needed for the tube to penetrate 75 millimeters.
3. Go.
A note is kept of all results. Not only does the test give information about ground strength at the bottom of the hole, it has also enabled a sample to be recovered. Notice the sampler has a cutter at the bottom to do this. Bob Risby opened it up.
Well, this is an SPT split sample taken from 3.2 meters. Top of the sample shows us a grey, slightly clay silt running down into a mottled, very sandy, stony clay. And this sandy clay has some pebbles or gravel in it.
Of course, the beauty of this is that it tells us exactly where that contact is, doesn't it?
That's right. Of course, we must allow for the fact that when we're taking these samples, sometimes the material does actually compress slightly, and we must never forget that.
So what's the story of Borehole 11 then, Bob?
Well, as you can see from the material we've recovered here, at the top of the borehole, from ground level to a depth of 1.9 meters, we've got this brick fill. And And below that, below the 1.9 down to a depth of 3.2 metres, we have this brown sandy clay. And of course we have an undisturbed 100mm sample in that, ready to take back to the laboratory for testing. And at 3.2 metres we then come into this very silty grey clay and then continue down into the mottled sandy clay with pebbles in.
And you're going to continue the borehole?
We will. We'll continue this borehole down to approximately 15 metres and let's see what we get later on.
And what they got later on was water. It occurred in non-cohesive ground, so another piece of drilling equipment had to be used, the baler. The baler is used for removing water and debris from the hole, whatever the type of ground. It has a flap valve at the bottom, which prevents the loose and water-laden deposits dropping out. This technique doesn't collect undisturbed samples, but useful information such as density and grading can still be obtained. And of course, water samples can also be taken. The contents of the bucket will be allowed to settle before the water is poured off and the sample bagged. Shell and auger is not the only means of drilling a borehole. This rig is being set up to deploy another technique, rotary drilling. It's rapid and well suited to drilling in hard rock, allowing depths of several hundred meters to be reached. However, the rig is expensive, making it more costly than shell and augering. To begin the process, a standpipe is positioned at the point where the hole is to be drilled. Although this equipment is installed on a lorry, it's possible to mount similar equipment on a barge or platform for drilling over water. And for more restricted areas, smaller, more portable machines are available. A cutting shoe at the bottom of the standpipe takes it into the ground. Once it has penetrated the topsoil, the opportunity is taken to collect a sample. As with all sampling, care is taken to make sure the sample bag is properly labelled. The standpipe is driven down further. With the standpipe in position, a hollow T-piece is added. The T-piece and plastic tube will form part of the flush flow system. So with this stage reached, what comes next?
Well, John, now that we've got the standpipe set, it's time to start open holing.
Open holing, or open hole drilling, is one type of rotary drilling, and it uses special drilling bits.
There are three basic type of bits that we've got to choose from. First of all, we have here the tungsten carbide stepped drag bit. This is a simple bit with 3 wings, stepped tungsten carbide face, and this bit is used in the softer formations for actually ripping the rock or tearing the rock from the ground. When it's down the borehole on the end of our drill collars, it's used in this position. As it's rotated, we have a hole down in the top here in which the flush, be it air or water, it is forced down the center of this bit, comes out of these holes at the bottom and blasts against the cutting faces, keeping them clean. The cut material then is pushed up the side of the drill collars and up to the top of the hole.
And then the second type of bit?
The second type of bit we've got is similar to the first type. It is a drag bit, except rather than the teeth being made of tungsten carbide, they're made of polycrystalline. Very hard man-made material, as hard as diamonds, and this bit is also used for tearing at the rock, but is more suitable in harder formations than the standard drag bit. Again, we have holes on the face of the bit where the flush is expelled from, and that flush is against the face of these cutting teeth, keeping them nice and clean. Polycrystalline bit. It's not used very much in civil engineering because these are very expensive. Each one of these little cutting discs costs about £100, so you can imagine it's a very expensive bit.
And finally?
Well, finally we've got the bit which I suppose most people will recognise, and this is a tricone rock roller bit. And it's the sort of thing that they imagine is used on the North Sea in oil exploration, but it's also used in civil engineering. It's a bit made of 3 milled teeth attached to bearings onto a body. This particular bit cuts the rock by a crushing action. Rather than the drag bit that tears away at the rock, this actually causes a crushing action. And as the bit is rotated at the bottom of the borehole, you can see these wheels rotate and crush the rock. The flush again is pushed down the centre of the bit, comes out at the bottom here and blasts away at the rollers, moving the cut material around the outside of the bit and up the borehole to the top. This particular bit is very coarse teeth and is suitable for soft formations, but the teeth can be made finer and they can be made of harder material to suit very hard rocks.
And which one are we going to use today then?
Well, because we've got soft comb measure formations, then today we're going to use the standard tungsten stepped drag bit.
On this occasion, the drag bit is followed by this stiffened component, known as a stabilizer. A second stabilizer is then added to the first. The stabilizers help ensure that the drill bit is not deflected off course, so maintaining the borehole in a constant direction. Although they're connected together for surface drilling, when the hole has been deepened, the stabilizers will be separated by a spacer, putting them several meters apart. The drill bit isn't ready to go, however, until an all-important element is introduced. This is a pump, and it circulates the flush, which in this case is water. The water flows down the center of the drill string and right down to the bit at the bottom of the hole. It then rises up on the inside of the standpipe, bringing the cuttings with it. Water isn't universally used. Some ground conditions require other media, like air or foam. The drag bit is now drilling at full speed, and the flush is bringing the cuttings to the surface. And because the operators know the depth at which the drill is cutting, the material can be monitored and collected for later analysis. Also, the material gives the operators direct information about the type of ground they are drilling through. As with shell and augering, the sides of the hole can be supported by casing. You'll remember this has the added benefit of reducing the inflow of groundwater and the loss of flush. It's not long before the drilling head is extended as far down as it will go. Then the chuck is simply released from the drill rod and moved to the top of its travel. The chuck then grips the rod higher up and the drilling continues. But what happens when there's no more drill rod? This is the same technique, but at a different location. And notice they're using air flush, not water. They've reached the stage at which there's no longer sufficient drill rod above the hole. So the thing to do is add another one. With the new rod added, another cycle of drilling and rechucking can commence. Sooner or later, the drillers are likely to encounter water. This dip meter provides a convenient means of determining where the water level lies. The standard practice is to wait 20 minutes after drilling has ceased before measuring the water level. This applies whatever drilling method is used.
$290.
The water level must also be measured at the beginning and end of each drilling shift.
About 8.2 metres. So now we've finished the open hole drilling, Bob. What are we going to do now?
We're going to take a core now, John, and to do that we use this double tube swivel type core barrel. This particular one is 116mm diameter and it's a metric series, and it's a type of core barrel in common use in the UK today. The barrel is made up of two basic components, the outer barrel that you see here and the inner barrel. The outer barrel is connected to the core barrel head at this end, and you see the core barrel head has a thread on. When the core barrel head is rotated, that in turn rotates the outer barrel. We have a bearing system here which is connected to the inner barrel.
Yes.
And when the core barrel head is rotated, as you can see, the inner barrel stays still. And actually when it's down the borehole, that's how it works. The outer barrel with the diamond bit on is rotating, the inner barrel that the core goes inside remains stationary.
And this stops disturbance to the core while it's being taken, doesn't it?
Yes, that's right. Because the inner barrel's not actually rotating, the core actually slides up inside the barrel without being disturbed. Another feature here, you'll see we've got an O-ring at the top of this barrel. There are some holes underneath that O-ring connected to the inner barrel so that any water or air inside the empty inner barrel, as the core goes in, allows that water or air to come out of that non-return valve. Another feature of the core barrel head, if you notice, are some holes that are drilled in the core barrel head. Through these holes comes the flush. The flush comes in at the top of the barrel, out through these holes, and makes its way down outside the inner barrel, but inside of the outer barrel. So it's down the annulus between the two barrels, and our water is flushing down there when we are drilling. So let's close this end of the barrel up, and we'll go to the other end and show the coring bit and how that is fitted. Well, this is the bottom end of the core barrel, John. As you can see, we have the inner barrel here, and this is the one that is fixed to the bearing, so it rotates. But of course, when it's down the hole, that's the one that stays still, and it's actually the outer barrel that rotates. Now, you may remember that I described this as a double tube swivel core barrel. In fact, today we're going to make it into a triple tube swivel core barrel by inserting a transparent plastic liner inside the inner barrel, and this transparent plastic liner is used to retain the core in good condition when we withdraw it from the core barrel. Onto the bottom of the core barrel then we fit the core lifter case, and this fixes onto the bottom of the inner barrel. Inside the core lifter case we have a core retaining spring. This is a wedge-shaped spring that's used to jam the core into the barrel as it's recovered from the hole.
And of course this stops the core from dropping out of the barrel once the barrel is withdrawn from the hole.
That's right. Whilst the barrel is going down and core is going in, the spring is in the up position like that as the barrel is withdrawn from the hole, so the spring comes down, wedging the core into the barrel. We just check that all that is running free before we put on the most important part of the core barrel, which is the diamond bit, which we're going to screw onto the bottom. As you can see, this is a circular bit and contains lots of little diamond stones. This particular bit contains diamonds of a size 10 to 15 stones per carat, and this is a type of size of stone that we would use for drilling softer rocks. If we were drilling a harder rock formation, then we might use smaller stones, maybe 40 to 60 stones per carat, or even 80 to 100 stones per carat. And for very hard rocks like granite, we would probably use impregnated diamond bits, which would be very small bits of diamond dust. But today in the soft rock formation we're going to use this 10 to 15 stones per carat bit. And we screw this onto the bottom of our core barrel like this. Another thing to note is you see the little waterways in the diamond bit. If you remember, we said the water is flushing down between the outer barrel and the inner barrel, and so it's coming on the outside of the core lifter case down these little waterways and washing all the cuttings back up the outside of the core barrel up the hole.
With the core barrel assembled, it's ready to begin coring. As with the earlier example, the objective is to obtain as undisturbed a core as possible, which is why the inner barrel does not rotate. The water flush removes material which doesn't enter the sample tube. With the coring complete, the core itself has to be removed. First, the cutter is removed. Next, the core catcher. That then gives access to the plastic sleeve. The core is carefully handled to cause minimum disturbance before it reaches the laboratory. At Geotechnical Engineering's laboratory, geologist Roy Harris gives his view of what the core has to tell us.
This is borehole 1, Roy, from 8 metres at the top down to 9.2 metres at the bottom. Let's see what's inside.
Yeah, the first thing we do, John, with a piece of core when it comes into the lab is to measure the total core recovery, and in this instance you can see that we've got slightly over 1.2 metres, indicating that we've got 100% core recovery.
That's very good, isn't it?
Particularly in a fractured mudstone of this nature, is very good. Sometimes we only would get perhaps 80 or 90% recovery.
And it looks as though the core's pretty well fractured.
That's right. One of the other things that we like to measure is the solid core recovery. which is the length of intact core without fractures. And there are so many of these cracks in this core, John, that we would just describe it as being non-intact. The other thing we're interested in is the rock quality designation, which is the length of pieces of core greater than 100 millimeters in length.
But again, at the full core diameter.
Yes.
Yes. So again, that will be 0.
0 again in this.
And then if we look at the lithology, the mudstone looks more silty at the top than at the bottom.
That's right, John. We've got the occasional ironstone nodule in the core and a thin carbonaceous mudstone band. And below this point, the core looks a bit darker. It could indicate it is slightly more carbonaceous here, and it is a lot, well, very weak compared with this core at the top.
Yes.
So it's been possible to determine the lithology, total core recovery and rock quality designation for this material. And that's been helped greatly by the plastic liner keeping the core in a near undisturbed condition. A chisel bit, and it's being used in one of the third methods of borehole drilling, continuous flight augering. It works like a large corkscrew with a solid central rod and corkscrew-like flights. The chisel is used in granular or stony soils and weak rock, but other bits can be used depending on conditions. The flights carry the drilled material to the surface, and because the operators monitor the depth of the drill, they know approximately where the material is from. This makes it useful for obtaining disturbed samples for description, grading and index testing. Once a length of auger has been drilled right down, it's easy to add another. It's possible to drill quickly, up to 50 or so meters an hour in weak rocks and superficial deposits, and the speed is helped by the auger supporting the hole without the need for casing. So, even though the equipment is more expensive than the shell and auger rig, the costs of drilling can be similar. This is another form of augering, hollow stem augering. It's more sophisticated in that it allows cores to be collected from soils and soft rocks. As in rotary coring, a plastic liner is put inside the central tube to help preserve the core. A cutting shoe is added. The core is then entered into the hollow stem of the auger. And notice at the top it has the same swivel mechanism as the rotary corer. So when it's boring, the swivel allows the auger to rotate while the central tube remains stationary. The cutting blades on the auger are tungsten tipped. In sections where a core isn't required, a full hole cutting bit replaces the corer, and it locks to the auger, so rotating with it. But on this occasion, a core is to be collected. As with continuous flight augering, the sides of the hole do not need the support of casing. This increases speed, but it also has disadvantages. Problems occur if water-bearing strata are encountered. With no casing to reduce or stop the flow of water, the hole floods, so churning up material. This can severely reduce the value of the samples. However, in this shallow hole, no water was encountered. The sample is retrieved by attaching a catcher to the coring tube. For a deeper hole, this would entail lowering the catcher down the hole. But however it's done, the core is recovered without removing the augers from the ground. Safely recovered, the core is taken for labelling and eventual dispatch to the laboratory. That then is an overview of 3 common techniques used in borehole drilling. You'll find further information on each of them in the notes which accompany this programme.